cosmic microwave background, or the CMB, is the earliest direct observation that we can make of the universe. It was first discovered in 1965 by Arno Penzias and Robert Wilson using the Holmdel-Horn antenna. They identified the signal as a radiation source coming from outside our galaxy that was uniform in every direction at a temperature of about 2.7 Kelvin, or barely above absolute zero. It was not until the Cosmic Background Explorer, or COBE, was launched in 1989 that the subtle temperature variations in the CMB were found. The temperature of the CMB is known to vary only by several hundred microkelvin from 2.7 Kelvin. This is akin to viewing the Earth from a great distance and being able to see that the surface is indeed not flat, but covered by mountains and hills that are nevertheless dwarfed by the diameter of the Earth. These temperature variations arose in the very early universe, when the entire volume of the observable universe today was condensed down to a size smaller than that of the nucleus of an atom. At this scale, quantum weirdness dominates the universe. Particles pop in and out of existence, exist in multiple locations, and deviate from behavior that we experience on larger scales. This quantum weirdness caused subtle variations in density. These variations in density correspond to the variations in temperature that we see in the CMB. Pockets of higher density would slowly collapse together by the force of gravity. These pockets of higher density would, over billions of years, form into the galaxies and galaxy clusters present in the universe today. Essentially, the structure of the entire universe has been formed by processes that operate on the subatomic level. The other main component of note in the CMB is its polarization. To understand polarization, remember that light is electromagnetic radiation. This radiation is composed of an electric wave and a magnetic wave, oscillating perpendicularly to the direction that the radiation is traveling in. The electric and magnetic waves can have different orientations with respect to the direction. Shown here are electromagnetic waves whose orientation varies by 45 degrees in each of the four figures. When all of the electromagnetic waves from a source of radiation are oriented in the same manner, that radiation is said to be polarized. CMB polarization has a magnitude of 1 part in a million, or about 1/10 the intensity of the temperature variations. Detecting this polarization was therefore a much more difficult feat, one not accomplished until the 2002 DAISY experiment. Polarization within the CMB can be caused by two main processes in the early universe. One is the very same density fluctuations that cause the temperature differences discussed earlier. The other is a phenomenon known as gravitational waves. According to Einstein's theory of general relativity, gravity is just the warping of space-time. You can visualize gravitational waves as a traveling disturbance in space, then. Gravitational waves can be caused by extremely massive and powerful objects and events. An example of such an event is two black holes colliding. In the early universe, there were no black holes. However, a theoretical process known as inflation, which may have occurred in the very early universe, is capable of producing gravitational waves. Gravitational waves are in turn predicted to produce a very specific pattern of polarization in the CMB, distinct from the pattern created by density variations. Observing the polarization of the CMB for this pattern is therefore a way of determining whether there were gravitational waves in the early universe, and subsequently proving whether inflation happened or not.